Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 2 on inscribed angles. Okay, so now we're going to start to get into the heart of this unit, right? And we're going to start to see different types of angles and how they relate to arcs and chords and diameters and radii and things like that. So let's jump right into it and start talking about the topic of the day, inscribed angles. In our first lesson on circles, we learned about various terminology associated with circles, such as radii, diameters, chords, and arcs, and central angles. In this lesson, we'll learn about inscribed angles, which are some of the most important in all of circle geometry. Let's bring that up to the top of the screen and talk about what an inscribed angle is. An inscribed angle is one whose vertex lies on the circle and whose rays both intersect the circle. All right, now that's important because there are certain types of angles that could have a vertex on the circle, but like whose rays maybe like extended then like out this way, right? We've got to have a vertex that lies on the circle and whose rays then also intersect the circle. Let's take a look at letter A. Name 3 inscribed angles and the arcs intercepted by those angles. Okay, cool. So let's take a look at one. All right, so again, an inscribed angle is an angle whose vertex lies on the circle and whose rays both intersect the circle. So here's a good example. Let me take a look at this particular angle. I'm going to highlight it like this. All right, that is an inscribed angle. What angle is that? Well, that's angle, angle DAC. Now, one of the most important things about inscribed angles are the arcs that they intercept. Now, what that means is that the arc that lies between where the two rays intersect the circle. So that is this particular arc, right? It intercepts arc DC. All right, that is one of the one of the inscribed angles of this circle. What I'd like you to do is see if you can find some others, all right? Now there's actually 4 total inscribed angles on this circle right now. I just want to get at least 3 of them down, all right? So pause the video now and see if you can name some other inscribed angles. All right, well, let's go with this particular angle. Let's go with angle ABD, all right? So angle ABD, and the arc that it intercepts is arc AD. All right, so that's a nice inscribed angle. All right, let me erase, let me erase that as opposed to just throwing it around the screen. Let's see, how about angle DCA, right? That's an inscribed angle. So angle DCA is inscribed, and the arc that it intercepts is arc AD. Okay. And there's actually one more. Let me get rid of this. We've got this particular angle, and that is angle BAD. It's a bad angle, and it intercepts arc BD. All right, and that's it, okay? So lots of inscribed angles in this particular image. Now let's take a look at letter B, which is quite important. Can 2 inscribed angles intercept the same arc? All right, well, what do you think? Pause the video and tell me what you think, yes or no. And the answer is yes, absolutely. In fact, right here. Those are 2 angles that intercept the same arc. So let's say yes, angle ABD and angle DCA both intercept AD. All right. But more importantly, you know, it's obvious that you could have multiple ones that intercept the same arc, right? In fact, if I just extend the page a little bit in free form, if I had some circle like this, and let's say I had some arc AB, Okay. You know, I could have a variety of inscribed angles that intercept that, right? If I had something like this, that would intercept that arc. If I had this, that would intercept that arc. This one would intercept that arc. All right, so it's very, very common actually for multiple inscribed angles to intercept the same arc. Now, why that's important, we'll get to later, all right? But for right now, the answer to that is obviously yes. All right, let's keep going. Now, there is a special relationship between the measure of an inscribed an inscribed angle and the measure of the arc that it intercepts. Before we explore this relationship in detail, we need to review an important theorem, the exterior angle theorem. Let me bring this up to the top of the page so we can talk about this. The exterior angle theorem. The measure of any exterior angle of a triangle is equal to the sum of the measures of its two remote interior angles. All right, let's pop this out for a second, right? So remember exterior angles. We saw this way back in, I think it was Unit 3, okay? But very, very simple. If I've got a triangle and I extend any one of the sides outward, it produces an exterior angle. And that exterior angle is always the sum of the two interior angles that it's not adjacent to. Not adjacent to. Those are called the remote interior angles. So in this case, the measure of angle 3 is equal to the measure of angle 1 plus the measure of angle 2. Now, I cannot even emphasize how important the exterior angle theorem is to most of the work that we do in this unit. It's going to actually be the bedrock theorem that will allow us to prove all sorts of things within this unit. So let's take a look, right? The exterior angle theorem, along with properties of circles, will allow us to conclude that the measure of an inscribed angle will always be equal to 1/2 of the measure of the arc that it intercepts. It's remarkable. So like when I intercept an arc with a particular inscribed angle, how large that inscribed angle is will always be exactly 1/2 the measure of the arc that it intercepts. Now what we're going to do is in the next two exercises, we're going to prove that theorem, all right? But let's start off with exercise 2 and prove it in a very special case. Exercise 2. In the diagram below, AC is a diameter. We wish to prove that the measure of angle BAC is 1/2 the measure of arc BC. All right, so before we get into letter A and letter B, let's just make sure that we get this, right? Here I've got this inscribed angle, BAC. All right, forget about M, forget about this extra segment drawn. Those are just what we're going to be using to do the proof, okay? I'm just trying to show that in this case, the measure of this inscribed angle, which is actually angle 1 or angle BAC, depending on how you want to name it, will be 1/2 the measure of arc BC. Okay, but this is a very special case, right? Because this is a case where one of the two rays of the angle happens to be a diameter. All right, anyway, let's now go on to prove this particular fact for this scenario. Letter A. Why is triangle BMA isosceles? What does it tell you about angle 1 and angle 2? All right, well, pause the video now and see if you can answer letter A. Well, it's isosceles, right? Because MB and MA are both radii and so must be the same length, right? So these two are both radii, so they got to be the same length, right? MB and MA are radii, so are congruent. All right, great. Now what does this tell me about angle 1 and angle 2? Tells me that they must be congruent themselves. This tells us that the measure of angle 1 must be equal to the measure of angle 2. And I could say that that angle 1 is congruent to angle 2, but given that all of this theorem is about the measures of angles, I want to bring that in right away. So the measure of angle 1 is equal to the measure of angle 2. Great. All right. Now let's take a look at letter B. Based on A and the exterior angle theorem, why can we now conclude that the measure of angle BAC is equal to 1/2 the measure of arc BC? Okay, so pause the video now and see if you can just think about why this has to be true given what we just saw in letter A, right? Given the fact that 1 and 2 are congruent angles. In fact, let's mark those right now. And given the exterior angle theorem. So pause the video now and see if you can figure out why this must be true. All right, well, forgetting about the fact that this is a circle, right? We know that angle 3 is an exterior angle of triangle BAM, right? And in fact, angle 1 and angle 2 are angle 3's remote interior angles. So by the exterior angle theorem, I'm going to do a little abbreviation here. By the exterior angle theorem, the measure of angle 3 is equal to the measure of angle 1 plus the measure of angle 2. All right. That would be true no matter what, right? But we know from letter A that angle 1 and angle 2 are equal to each other. That means that the measure of angle 3 must be twice the measure of angle 1, right? That's just because measure of angle 1 and measure of angle 2 are equal. But we can kind of flip that around a little bit now and say that the measure of angle 1 is 1/2 the measure of angle 3. And now we basically have it, right? Because the measure of angle BAC equals the measure of angle 1. They're literally the same thing. And the measure of arc BC is equal to the measure of angle 3. Now, before we kind of conclude this, let's just make sure that we really have this, including putting the M a little bit closer to the arc symbol. All right, this one's absolutely critical, right? Arc BC, its measure is defined, literally defined in our last lesson, as being the measure of the central angle that intercepts it. So that's the real key, right? BC has the same measure as angle 3. Angle 3 is twice angle 1. Angle 1 is therefore half of angle 3, so angle 1 must be half of arc BC, right? So altogether, the measure of angle BAC must be 1/2 the measure of arc BC. Kind of cool, right? So if this thing was, let's say, a 60-degree angle, right, BC, then the measure of angle 1 would have to be 30 degrees. If this was a 50-degree angle, that would have to be 25, etc. By the way, the relationship is oftentimes used in this direction, but often used the other direction as well. By the other direction, I mean if we knew the measure of the angle, then the arc measure would be twice the measure of the inscribed angle. So the inscribed angle is half the measure of its intercepted arc, and the intercepted arc is twice the measure of the inscribed angle that intercepts it. Now, you might be saying to yourself, but Kirk, right? That was a special case because one of the inscribed angle rays was a diameter. You know, what if it's not? Well, this relationship will always hold as the next exercise will illustrate, okay? So let's prove it now more generally. Exercise number 3. In the diagram of circle M, AD is a diameter. We wish to prove that the measure of angle BAC is equal to 1/2 arc BC. So now let's take a situation where one of the rays is not a diameter, right? So forgetting about that diameter for a minute, right? I'm just trying to now prove that the measure of angle BAC, that particular inscribed angle, okay, is 1/2 of the measure of its intercepted arc BC. Okay, well, let's take a look at letter A. Based on exercise 2, the one that we just did, what can we say about the measure of angle BAD and the measure of angle DAC? All right, so in other words, what I did is I took this particular angle and I drew a diameter in between it, right? Breaking it up into 2 cases, just like exercise number 2. Well, since we just proved in exercise 2 that when one of the 2 rays is a diameter, we get this relationship, I can now say that the measure of angle BAD is 1/2 the measure of arc AD, and the measure of angle DAC is 1/2 the measure of arc DC. All right, and I can say that directly because I proved it in exercise number 2. When one of the two rays is a diameter, we know this relationship holds. Now, letter B, use A to algebraically prove that the measure of angle BAC is equal to 1/2 the measure of arc BC. All right, so now what's really cool, right, is watch how this is going to go, right? I can now say that the measure of angle BAC, forgetting about the circle, right, I can now say that's equal to the measure of angle BAD plus the measure of angle DAC. All right, that's just the whole is the sum of its parts, right? That would be true whether we're in a circle or not. But from up above, right, I can say that using the principle of substitution, that the measure of angle BAD is 1/2 the measure of arc BD, and the measure of angle DAC is 1/2 the measure of arc DC. Okay, simple enough, right? Just using what we saw in A. Now what I'm going to do is I'm going to factor a 1/2 out of both of these, and I'm going to say the measure of angle BAC is 1/2 times the measure of BD, arc BD, plus the measure of arc DC. Okay, but if I add the measure of arc BD to the measure of arc DC, I of course get the measure of arc BC. All right, so the measure of angle BAC is 1/2 the measure of arc BC. And that's what I was trying to prove. Now there is a third case that we haven't seen yet, and you may play around a little bit with that on the homework, that would actually require you to do some subtraction of arcs instead of adding them. But regardless, one of the most important theorems in all of circle geometry is the inscribed angle theorem. The measure of any inscribed angle will be equal to 1/2 the measure of its intercepted arc. Okay, very, very important. Whatever your inscribed angle measurement is, however big it is, it will always be 1/2 the measure of whatever arc it intercepts. So let's play around with that a little bit in exercise number 4. In the diagram of circle C shown, HF is a diameter and intersects chord EG at point I. If the measure of arc HG equals 128 degrees, and the measure of angle HIG is equal to 100 degrees, find the following. All right, well, before we do any of these things, finding any of them, let's get some things down, right? The measure of arc HG is 128 degrees, so I'm going to put that right here, and that was a little bit weird. Let me just lock this down real quick so it doesn't move on me. There we go. So HG is 128. HIG, which is this angle in here, is 100 degrees. Great. Okay. So the first thing I'm asked to find is the measure of arc GF. Okay. Now that has nothing to do with the inscribed angle theorem. All right. Pause the video now and see if you can figure out what the measure of arc GF is. Okay, well, the cool thing is, right, is that we know that HCF is a diameter, or HF is a diameter, if you will, all right? So that means that the measure of arc HF is 180 degrees, so the measure of arc GF will be 180 minus 128, right? So 180 degrees minus 128 degrees. Watch that, right? Because that will come up quite a bit where you're given a diameter or something like that. You're given one arc that creates the semicircle. You need to find another arc, just subtract from 180. Now let's take a look at letter B. The measure of FHG. All right, so here we finally get to use our theorem, right? Now, given that I've already found the FG is 52, right, I'm looking for that inscribed angle, and that inscribed angle intercepts arc GF, right? So this is going to be 1/2 the measure of arc GF. So that's going to be 1/2 of 52 degrees, and that is 26 degrees. And I might as well write that in as well, right? We know that's 26. Let's take a look at letter C. The measure of angle EGH. All right. Now you might think to yourself, well, the measure of angle EGH, that's an inscribed angle. I just have to do 1/2 of that arc. Well, I don't know that arc. So pause the video now and see if you can figure out how to find the measure of angle EGH. Well, the cool thing is, right, EGH, which is this angle, is just the third angle of a triangle, 2 of angles of which we already know, right? So I can just use the fact that the sum of the angles in a triangle is 180 to say that this is 180 degrees minus 100 plus 26, right? Those 2 other angles. So that's 180 degrees minus 126 degrees, which is going to be 54 degrees. All right. And again, if I figure out an angle in these problems, I'm putting it on my diagram. All right, let's take a look at now letter D. The measure of arc EH. Okay, well, pause the video and see if you can figure out what the measure of arc EH is. So now we want to use the inscribed angle theorem, but kind of in reverse, right? So this angle, right, the measure of angle EGH would be 1/2 the measure of arc EH. Therefore, the measure of arc EH must be twice the measure of EGH, right? So this is sort of running that inscribed angle theorem backwards. The measure of angle EGH, what we just found, so that's 2 times 54 degrees, and that's 108 degrees. So this is 108 degrees. And finally, to come full circle, literally and figuratively, letter E, we want to find the measure of arc EF. Why don't you pause the video now and see if you can figure that out. Well, again, we've got this diameter, right? We have one arc that makes up the semicircle, 108 degrees. We want EF, so all we need to do now is 180 degrees minus 108 degrees, and that's going to be 72 degrees. And that's it. All right. So lots and lots of different pieces here. The only places we use the inscribed angle theorem were here in letter B and here in letter D. Everything else we used were either things like, the whole is the sum of its parts in terms of arcs summing to be semicircles or 180 degrees, or, right, the sum of the 3 angles of a triangle also being 180 degrees. Let's take a look at one more problem along this line. Exercise number 5. In the diagram of circle K, RS is a diameter, so we got another diameter here. Point T lies on circle K such that the ratio of the measure of arc RT to the measure of arc TS is 2:7. Letter A. Determine the measure of angle TRS. All right, so let's first make sure that that we know what we're trying to find. We're trying to find the measure of angle TRS, that angle. All right, in order to do that, what we absolutely positively must have, right, is that particular arc length. Or not arc length, but arc measure, okay? Now, we do that by utilizing this ratio. And we're going to see ratios like this come up a lot in circle geometry work. Lots and lots, okay? So there's a common method to doing this. Here's what we're going to do, all right? We're going to let the measure of arc RT be equal to 2x, and we're going to let the measure of arc TS be equal to 7x, all right? That ensures that no matter what x is, the ratio of these two arcs is 2:7. Now, those two arcs, RT and TS, must add together to be 180 degrees. So I can now say 2x plus 7x is 180. 9x is 180. Divide both sides by 9, and x is 20. Now the cool thing about that is that then tells me that RT must be 40 degrees and TS must be 140 degrees, right? And that is all I needed, right? I just needed the measure of TS, so I can now say the measure of angle TRS is 1/2 of that 140, and that is 70 degrees. And that's it. But this little trick, right, when I see that ratio, that's going to come up in probably just about every lesson we see from now until the end of this unit. So when you see something like a ratio of 2 to 7 or even a more extended ratio, start slapping some x's on there and see if you can set up an equation that way. Now, final piece, letter B. Explain why angle TWS must have the same measure as angle TRS. So why would this angle right here have to also be 70 degrees? Pause the video now and see if you can answer that question. Well, it's pretty simple, but very, very important, right? Both angle TWS and TRS intersect or intercept the same arc. And because they intercept the same arc, and they have to be half that arc measure, then they must be equal to each other, right? They intercept the same arc. So, must be the same measure. And it doesn't actually matter that they both must be equal to 70 degrees. In fact, we can really state sort of an additional theorem right here, right, or a corollary to our theorem that we had before, which is if two inscribed angles intercept the same arc, they must have the same measure, right? And it makes sense, right? Any inscribed angle will be 1/2 the measure of its intercepted arc. So if two inscribed angles intercept the same arc, then by calculation alone, they're going to have the same measure. And that's actually a relatively important theorem. Okay, so let's wrap it up. Now we learned a variety of new things today, not the least of which was simply the definition of an inscribed angle. You know, this idea of an angle whose vertex is on the circle and whose rays then extend out and intersect the circle, both of them, right, in two different locations. Now, the other real important piece that we saw, obviously, was that the measure of any inscribed angle will be 1/2 the measure of its intercepted arc, all right? And that is absolutely critical. We'll see that kind of come up time and time again in this course as we move on. For right now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.